All right, line N1, we're in learning task number 1. There is only one in this one, and that is going to be describe renewable energy systems. And we're going to go through the basics of all of these systems. We don't have a lot of them that we connect really here in British Columbia. And that's mostly due to the overabundance that we have of cheap hydroelectric power. In a lot of other areas of the world, it's a lot, they just don't have those resources of having the mountains and all the lakes and the mountain ranges and valleys that we just end up damming up over here in British Columbia, storing water behind there, and then converting that to electricity. So other places that are burning off of coal or off of natural gas or nuclear, they're using nuclear reactions to go and heat water to create steam. All of these things are expensive types of systems. Ours is a fairly passive one, and so it's quite cheap. So we don't see a load of these inside of British Columbia. That being said, they are widely used throughout some of the other parts of Canada. Prairies where things are really flat. They don't have the same valleys to hold water. Ontario and the Quebec and places like that where they have a lot more wind and a lot more solar energy that's going to be generated. The Alberta and Saskatchewan use a fair bit of wind because they're so flat. They get a lot of air movement on there. So you will hear about these in other areas, and because what you're eventually going to be writing, your interprovincial, is going to be a national test, there needs to be some knowledge of these systems for you. Let's start by talking about what exactly is a renewable energy system. They are going to go and all have a characteristic of not emitting greenhouse gases in the process of producing electric power, or not emitting more greenhouse gases. There are some heat-based ones that are going to go and take naturally reacting heat types of things, where we have got like composting type of action or dissolving different solids to go and form methane, etc. That's stuff that would happen naturally. We're not accelerating, we're just capturing it and using it. So it is termed as being renewable energy, although it does produce some greenhouse gases in the process, but we're just capturing and using those. A lot of our renewable energy can be direct, where we're going to be taking photovoltaics. We're using the energy from photons to go and create electricity. Others are going to be indirect, where we are using natural cycles of water, precipitation, wind, and things like that on our dams and our wind turbines. There is also going to be this big difference between distributed generation and remote power. And distributed generation is not big here in British Columbia, but California and Hawaii are absolutely huge on this concept of distributed power because they both have a fair bit of sunshine and not a lot of, massive mountain reservoirs. Lots of water around Hawaii, lots of water off the coast of California, but the problem is it's not up high where it's going to be flowing down. It's as low as it's going to get. It's at sea level. So what they end up doing is they end up creating these grids that are going to be referred to as distributed grids. And so I'm just going to draw a whole pile of houses over top of here. These are houses that are poorly drawn ones. And what they'll do is inside of each one of these ones, and there's big companies, huge companies that go around and they knock on people's doors and they offer to sell them a PV array, photovoltaic array. And so these people will put one up on their house. And part of what they have on their photovoltaic array is they're going to be generating power. Now, these companies have got contracts with the state of Hawaii or state of California or some of these other, ones, Nevada, Utah, some of these other really dry, hot ones have these. And these companies have got a contract to supply X number of kilowatts to, the supply authority that they have over there. So what they have is distributed power. So we're going to say that these ones here are with group A, these ones here are with group B. We'll make these ones a couple of A's, and we'll make this one a group B type over here. What they do with all of these is these all get tied in through a net metering onto the main power grid. And it's a two-way stream of electricity. So each one of these is able to go and take off of the grid, but each one is also able to supply back into the grid. You got to think that in a lot of places where we've got high density housing, apartments, there's only one roof for, dozens and dozens of households. So that electricity that is generated out in the suburbs by, utilizing that roof space, which is clear, doesn't have trees over top of it or anything like that, becomes quite valuable real estate. People place these on top of there. What happens is they use from this, and any excess that they're not currently using gets generated and sent back onto the grid. It gets tied to this, and so now the grid is going to be able to be fed by that, so that if you have somebody else, we'll take this one over here, that doesn't have a photovoltaic array on it, they're able to go and take from that actual grid. Also, if the photovoltaics on top of these houses are not, generating enough power to run everything that's inside of the house, they can be, running the bulk of it, and then the rest of it would be coming in from the grid itself. This is what's referred to as distributed generation, where we're having many, many houses that are going to be synchronized together. It's all controlled over Ethernet and data that are then going to be used to supply a grid. Less common out here, more common in drier, hotter places, and places where they just don't have those same resources as we do. All right, remote power is going to go and be generally for standalone. Here in British Columbia, we do have a fair bit of remote power, and usually it's going to be associated with like cabins and off-grid types of housing. Where somebody has got something that is built quite a ways out, and it's just not worth the time and the expense of getting a actual hydro line brought out to it. And so as a result, they just go and place their own system onto it. Remote power systems will be standalone. They're not going to be grid tied. What we have over here is referred to as a grid tied system because every one of these ties back into that grid. Remote ones will have to be by themselves, and they will require some sort of energy storage, right? So that you're going to be able to go and hold on to some of that power when you run out of wind or run out of sunlight. Usually we will store it in batteries directly as electrochemical storage, or other ones we will go and utilize is going to be what they refer to as like a microhydroelectric, where you are going to go and have photovoltaics that are going to be active during the day. Those photovoltaics, let's say that somebody has got a cabin by a small remote lake, they're going to use those photovoltaics to go and run a small pump that's going to be inside of here. It'll all come off the photovoltaics and go to the actual cabin itself. But they'll run a little pump that's going to be inside of there. That pump is going to go and pump water up the hill behind the cabin to a reservoir. That reservoir will have a runoff so that, this thing is constantly running year round. You're going to be filling that tank so that it's always going to be all the way full, and the runoff just runs back down to there. It's fine. It's free energy, so you might as well utilize that. But then what you'll have coming out of the bottom of that tank is you're going to go and have a small turbine that is also going to be able to be tied back down into that same overflow line that's going back down to the lake there. And anytime that there's either no sunshine or it's night, then you're going to be able to turn this on. So you just open up a valve that's going to start spinning the turbine, and the turbine is then going to go and generate electricity that is then going to go back to your cabin over here. If you're only utilizing this thing infrequently, it's a fairly useful one. There are larger scale ones of these. Hawaii's got a number of these, because the available amount of coastline, because they got such steep mountains, like right down to the water's edge, it makes it really easy for them to get the elevation gain to go and drive these hydroelectric ones. All right, let's talk a little bit more about the wind power. Wind power has, we used to just use, wind with windmills to actually physically drive stuff. Now what we do is we go and drive a generator, which we used to drive equipment. We are distinctly split into two main classes. We've got small wind and large wind sections. Inside of section 64, we're going to have a small wind, which could be either a single turbine or an array of turbines. That is going to be up to 100 kilowatts, and anything larger than 100 kilowatts is going to be a large wind system. Once again, it could be a single or multiple itself. Power conversion devices are going to often happen right up at the top inside of this section that over here. That's going to be called the nacelle, that section. They look really small from, down here. Once you actually get up top there, they're going to be the size of like a, garage on a lot of these large ones. Just a massive, massive building that's up top there. And we're going to go and have the actual generator. We're going to go and have inverters, charge controllers. Oftentimes, pretty much everything is up top there, so that all we need to go and do is carry lines back down from this. Now, this one here is a small. It's only 5 kilowatts. But the very, very large ones that you see, those nacelles are massive, and they contain a load of different stuff that's going to be synchronizing with others, etc. North Sea, just off of the coast of Holland, I've got a cousin that works out there, and he works on these ones for a massive company that's out there, and they run these gen sets up in the sky. They've got them all tied together on the seabed, and he said that the amount of space when you're actually up there, he said it's like bigger than his apartment that he has. So yeah, kind of cool. It's a massive, massive thing. We just lose sight of it from the ground. A lot of ours are going to go and be these vertical ones. I'm sorry, not the vertical ones here. These are the horizontals. This is the vertical ones over here. Vertical ones over here have got a little bit of an easier time in the wind. When you take a look at these ones here where we've got a horizontal axis, what it is there's a lot of leverage. If you take a look at the fan blades themselves up top act as if they were a point of leverage. So any wind that's being pushed up against that is trying to bend this tower over, and so they result in having to have some massive, massive anchoring issues. Vertical towers over here are going to be easier to go and anchor because that force is now being distributed all the way along rather than just all the way up top. This one over here is going to go and see a lot more leverage. These ones over here see a lot less leverage. H-gyro, Darius rotors, they're all just different types that we are going to have. We do see these really large ones as well. These things have actually fallen a little bit out of popularity. People are worried about the number of birds that they kill and, the sounds that they cause. They do cause a very low frequency, kind of thrumming noise whenever you're going to be by these things. And it's just the fact that we have got air that's pushing by and there's always going to be a little bit of vibration. Wind turbines also are not fully effective. They're very good. They move fairly well. But for me to have a 100% effective wind turbine, I would need to have a solid disc. And if I've got a solid disc, I'm not going to have the airfoil, and the blades themselves are going to go and turn. So there's a whole science to developing the blade angle and pitch and, all of that goes along with it. Ultimately, they are never going to be 100% efficient. They're actually fairly low efficiency, but, if there's a lot of wind and that wind is free and the payback time makes sense, absolutely. Do not ever try to go and place one of these without engineering help. You might have a customer that might have bought one, certified or uncertified. Make sure that even if it's going to be a small residential unit like this, that they get somebody else to engineer the footing and the support. The electrical hookups provided at CSA, you should be fine with. Just don't try to engineer that stuff because you have to know the physics of the loading of these. All right, photovoltaics. Everybody has heard about, solar power. Technically speaking, these are called photovoltaics, so we will refer to these things as PVs in our trade over here. Solar cells are going to be an individual component that is going to go and take light, convert it to electricity, send it out to a load, and then it takes those electrons back in. Remember, we still have to complete a circuit, right? It's not that the electricity just flows out from this. The electricity has to flow back into these ones over here. Individual cells themselves are going to go and be small amounts of voltage, about 0.6 volts that we are going to see off of the individual cells. So what we will usually do is we'll take all those cells and then we will go and place those into a module. So this over here is an individual cell. The module itself is going to go and have all the interconnects so that these things can be series together to go and increase the amount of voltage, and then they can also be paralleled so that we are then going to be able to increase the amount of current that's going to come off of them. All of our photovoltaics work off of just basic semiconductor conduction. Let me just draw one out over here. You should be familiar with your diodes from first year. You covered those before, where we had two chunks of semiconductor, which is going to be 4 valence electrons, and we are going to go and take those two chunks of semiconductor, we're going to dope them individually. I'm going to go and have one type that is going to become an N or a negative type, and that's going to be when I pentavalently dope it. Pentavalent, meaning that I'm going to go and have 5 valence electrons. The other type is going to go and become a P type or a positive type, where I'm going to go and trivalent dope it. Okay, really when you take a look at it, semiconductors made up of 4 valence electrons. That's what these things would be balanced. Over here, we're adding an excess of electrons, which means that we're going to go and have a excess of negative charge compared to the trivalent, which is going to be where I'm adding in, some 3 components. So I'm lowering the total number of electrons. So I'm going to be a slight bit more positive. I've got more holes over there. So the N types have got extra electrons. The P types have got extra holes. What happens is when I place these two together up against each other, they're going to go and exchange some electrons for some holes right at the junction. And when they do that, what's going to happen is we set up what's referred to as the barrier potential, or the depletion region that we will have right inside of there. And the depletion region is going to go and have a small voltage that is going to be placed across it in the opposition to how we would normally run these. Now, this is still a diode we're describing here. We're going to change it to a solar cell in a minute. Excuse me. But let's still continue describing it as a diode. For a diode to go and conduct, we would have to go and attach a positive here. We would have to go and attach a negative here. That would then be overcoming the small positive here and the negative here. This small positive and negative over here is the depletion region itself. It's what we refer to as the barrier potential. And as long as whatever we are putting across the diode is going to be larger than that depletion region, we will be able to force this thing into conduction. Usually it's going to be that 0.7 volts that we would have. That's the normal way that we would go and create this, right? This over here is a small balanced amount of voltage that we are going to go and have inside of here, where we are going to go and have trivalent and pentavalent components over here that are going to be tied together. Now, trivalent components does mean that they have got 3. And so when I get a photon is going to be a massless particle, I know it screws with your mind, that is emitted from the sun. It's going to be light particle. What happens is we have a really thin end layer, we have a fairly thick P layer over here, and we are going to go and bombard it with photons. And when we hit our electrons that are going to be inside of this really thin layer, it will go and drive them through. You know, that photon doesn't go and contain mass, but that photon will go and possess enough energy that it's going to go and transfer to drive an electron through. On this side over here, it is trivalently doped, which means that it is still in balance. Yes, we have removed some. It's a slight bit more positive, but it is in balance. And so what it's going to do is now we've got an extra electron inside of here. It's disturbing it. It's, disturbing the equilibrium. So if we connect a load across from the bottom part, the P over here, to the end part, that electron that was just knocked free by this photon over here is going to be able to travel through and back to this side, which is where this thing originally came from. We're basically just using photons to knock electrons over top of a barrier potential, and then the electrons say, hey, I didn't like that. I will use this load to go all the way back to where I came from. That's all it is it is a photodiode, or a diode that is activated by light that we are going to have that's going to go and knock electrons through, and then we just complete the circuit on the outside to go and create that. Remember how it said that each of these solar cells was approximately 0.6 volts? That's because that's the barrier potential that we're seeing. 0.6, 0.7 volts that we are going to go and have for the barrier potential off of these. You can't use a regular diode as a solar cell, for those of you that were getting really excited. The regular diodes just aren't clear enough. These are going to be extremely thin N types of layers, and then we're going to go and have the P type of layer on the bottom. The other thing that we see is these bars that are up top are going to go and be small conductive bars with these lines that are going across here. What that allows us to do is that allows us, if this is the top side of my solar cell, that allows me to go and take those electrons that I'm passing through my load and distribute them back in, right? If I only just have one point inside here, it's going to be hard for them to go and distribute through the rest of the cell. You'd end up with like unequal voltages. So what we do is we take our distribution point back to one of these bars. These bars are all going to be tied together. We take it back there, and then it can easily run along any of these conductive bars and spread out. Bottom side of the solar cell is going to go and have a solid piece across there. This one's got a grid because we obviously need to be able to let light through. More effective would be solid, but the problem with the solid is then light can't get through. Okay, that's the science, the basic science that's going to be behind these things. There is going to be a couple of ways that these are going to be engineered. We're going to go and have our IV curve. And IV just refers to I as current and V as voltage. It's going to be my volts versus current curve that I'm going to go and have. And it's going to be based upon a number of factors, such as temperature. The colder that a solar cell gets, the more efficient it's going to be. Irradiance, that's going to be the intensity of the light that's going to be hitting it. And air mass. Air mass is going to be based upon basically how obliquely we're striking the solar cell. And we're going to talk about that here in a second, once we get past that over there. It's the spectral distribution, or basically the wavelength, that we are going to be looking at. When we take a look at a solar cell, if I have got no current, if it's an open cell, so I have no connection going across, we'll just remove that. Ooh, that's not an eraser. If I remove that over there, we would then have open circuit voltage that we would be able to go and measure across. No current, it's going to be an absolute maximum. As soon as I place a load across there, I'm going to be able to start to flow that. And the lower the amount of impedance from my load, the more current I'm going to be able to flow through. And ultimately, if I were to go and short circuit that cell, so right over here, I'm going to have maximum amount of current flow that's going to be generated with minimum amount of voltage. That's what this curve over here is showing us. Now we see that this thing is going to go and give us a maximum amount of current. We see this ISC. It's abbreviated as being I short circuit. It is different than the way we think about short circuits. We think about short circuits as being absolutely terrible. This is basically just taking it to the max, kicking it to 11, whatever you want to call it. This ISC over here is just the maximum current that we can go and put out of there. Us shorting this out will not overload the solar cell itself. At the solar cell. The wiring and everything downstream, absolutely. We've got to watch out for short-circuiting that. But the solar cell itself is going to have maximum current that it'll generate, and it can do so safely. We are going to go and have VOC. That's going to be my voltage open circuit as well. There's also going to be a power curve that we are going to go and have. And the power is going to be a power versus voltage curve that we are going to have. And really what it is we are looking at right now if my voltage is going to be at a value of 0 versus my voltage, which is going to be VOC over here. That's these 2 points. And if we would have had this curve over here, we are going to go and have maximum current at this point with minimum voltage. So if you say power is equal to E times I, we'd say 0 for my voltage, maximum current, my power is going to be at a value of 0. We move a little further along, my voltage is a little bit higher, my current is still really high, so my voltage is a little bit higher, my current is a little bit high, we multiply them together, we see a rising. And so what we see along here is that as long as this stays more or less linear, my power is going to be rising, but then as it starts to slope down, we're going to hit this point where we are going to go and have a maximum power. And the maximum power is going to be entirely based upon the actual solar cell that we have. What this is developed from is it's just developed from an overlay of these two that we are going to have. And we can then go and figure out a maximum amount of current, that we are going to go and get at our max power peak. What we do is we overlay these ones over here. We find where our maximum power is. So we take that off of the other curve. We overlay that over top of this one. We drop that one down to this curve over here, which is going to be my IV curve. And then we can read that off of here, which is then going to go and tell us my maximum current that I'm going to have, or peak current that I'm going to have. We want to stay operating at the peak. And the peak is all going to be defined off of, that's, once again, irradiance. That's going to be the strength of the electricity that's going to be hitting it, the temperature, and the air mass. Let's just briefly talk about air mass. Over here in the northern hemisphere, that's where we are, we know that the Earth tilts, right? And so in the springtime and the summer, if we take a look at the sun, here's us on the Earth over there, we have ourselves tilted towards the sun, and really what's happening is that we're going through less air. Air filters, air cuts down on the amount of light. I want you to think about a sunset right now. Why is the sunset red? Well, because during a sunset, what's happening is the Earth is rotating, and we are currently, seeing all of that light that's shooting obliquely through the atmosphere to us. We're, right about here, just about to go into the shadow side of the Earth during our rotation. And what we're seeing at that point is just lots and lots of oblique, or, running kind of diagonal through the atmosphere to get to where we are. If I were to go and take a look at it like that, we see it's a long length like that because we're just about going over the curve. So it filters the light, and we get less heat. Everybody knows it gets cooler at sunset. We're going to get a change in the spectral distribution as well. The reds are going to go through, the blues, and the really, really high frequency colors of light start to get attenuated out of it. Excuse me. In the northern hemisphere, we always have got a little bit that we're tilted away from the sun. Even during our summer, it is not going to be perfectly straight on. That's the equator. That is going to go and have an air mass of 1.0. Because the equator is always going to be directly lined up with our sun over there. We're going to be a little bit further north, so we're always cutting through the atmosphere a little bit obliquely, so we always have got just more air to cut through, and we get less, power. We get less of our blue high frequencies that are going to be making it through. That's why we, for testing in Canada, have to go and have everything tested to an air mass of 1.5. It just standardizes, because if I give you data from a solar cell that's at the equator versus a solar cell that's in Canada or Norway or something like that, it is going to be completely different amounts of power that we are going to generate. Equator ones take a loss on the temperature, but they take a massive gain on the amount of irradiance. We get a slight gain on the temperature, the fact that we're colder, but we lose on the actual irradiance. Okay, panels for these ones here. First thing that you do when you see a solar panel is you look for that. If you don't see a CSA or a ULC listing, don't put it in. You don't know who's manufactured it or what standard they have manufactured it to, so you've got to be careful with that. There's another symbol that's on top of here that you should also be familiar with over here, that thing with a double box. That means double insulated. It means that whatever I've got that's live is going through, one set of insulation around, and there's going to be another set of insulation around it as well. It's a safety thing that you should have for each one of these. Reading off of this, you should be able to pull out a couple of different values. Maximum power, Pmax, we pull up that 185 watts. This is all based on irradiance of 1,000 watts per square meter that we're having. And a spectrum AM. Spectrum AM is going to be air mass that they're talking about, a 1.5. That's what we're supposed to have over here in Canada. And a cell temperature of 25. In other words, this thing has been tested to spec. You always want to make sure that it's been a spec tested one. Stuff that you buy off of Amazon or that your customer picks up from Canadian Tire or places like that sell, solar cells and stuff to people, is in often cases not going to be rated for these, so they will not be able to get, the rated 185 watts out. This one would give us 185 watts over here. If I stuck it on the roof of an RV, if I owned one of those machines and drove it down to Arizona, I would be able to get even more out of it. Open circuit voltage, in this case over here, 44.8. Short circuit current, in other words, the maximum current that I can go and pull out of that thing, 5.47 amps. And then maximum power voltage and maximum power current over here, that's going to be where I'm going to be operating this thing at. This 36.5 and the 5.09. Those are this intersecting point right over here. So they're taking the voltage off of that point. They're also taking the current off of that point. All right, let's talk about hydro systems. We work off of what's called renewable energy here in BC. We're just used to calling it, regular energy. But all of ours is termed to be renewable energy because it's coming from evaporated water, forming clouds, forming rain, the rain running down the mountainsides, gathering in valleys. We dam off the valley, and then we run it through a turbine. So it is considered to all be part of our hydroelectric systems. Number of different turbine styles that we are going to go and have. We are going to go and have impulse turbines versus reaction turbines. Impulse turbines work off of a jet of water. So water being directed in up against this. This is a Pelton turbine. It's been taken out of a machine. It's massive, massive beast over here. But where I'm going to go and have jets of water that are going to be directed into these. And as a result of it hitting that, it's going to go and, push backwards. Take a spoon and hold it underneath your actual faucet, and you can feel that sort of impulse that you're going to go and have. Now think about having a whole wheel of spoons, and it's the exact same thing. The other types that we have are going to be referred to as reaction turbines. And reaction turbines are going to be a flow of pressurized water to rotational kinetic energy. This one, you need to think about your sink as well. Now think about if you filled the sink up and if you drain it, that water is going to go and circulate around the actual drain hole as it goes out, and which forms a rotational. So that's what these ones here work off of, is they work off of a draining water. We're going to place them in the bottom of a body of water. We're just going to drain through them, which is going to go and cause that spinning. The spinning, by the way, is caused by, Earth's rotation. That being said, these types of turbines, Francis and Kaplan turbines, are going to be northern hemisphere and southern hemisphere types, and they're going to be more efficient the further north you are, the further south you are, because at the equator you have less of that rotational. It takes more to get it going compared to up here where we're further up towards the North Pole. So these ones, if you are buying anything that is going to be a reaction type of turbine, particularly when you are buying it off of, once again, Amazon or AliExpress or any place like that, you need to make sure that that thing is engineered for the northern hemisphere, because otherwise you're going to put this thing in and it's just going to kind of chug along and do not a whole lot whatsoever. Okay, let's talk about the overlay. Overlay for these ones is going to be done all the same. Now, this could be a dam that we would be looking at, or this could be a small micro hydropower system. The big difference between a dam and a micro hydropower is that a dam would actually be all the way across over here at the spillway, so we would completely block that off, store all the water behind it, and then we would have a spillway, which is just going to be when the dam is full, the water can go over the top of that dam that we are going to have there. That would be a dam system. A dam system stores all the power, and then we take all the water, and then we take the water out of there, and the dam system usually loses the canal and the forebay. What we would have is we would have instead just the penstock, the tube, that would come right out from the base of the dam and would go all the way down to wherever your powerhouse would be. That's for a complete dammed type of system. When we are dealing with micro hydropower, that's going to be smaller scale systems that are not allowed to dam off the river. Look at the amount of regulatory shenanigans that had to happen before Site C managed to be approved up north, right? It's a huge, massive hydroelectric system. It's really good for our economy because we generate a lot with, doing very little off of it. But there was a lot of regulatory, issues because that whole valley had to be dammed off. We were going to flood out a whole valley. There was wildlife. There was heritage sites. There was, people that had been made businesses and farms inside of there. All of that had to be moved and, compensated for. It was a big shenanigans. Micro hydropower is going to be just diverted. We're not taking the actual stream away. Anything that comes out of the stream is going to go back into the stream. We're just diverting. So we'll have a small canal over here, the weir. Usually that's going to be a gate that's going to prevent, sticks and things like that. That canal is going to go down into a tank. We call that tank the forebay. The tank is usually going to go and be a covered type of tank. They're showing these things as being open, but usually we want to cover this thing over. And then out of that forebay, we are then going to go and have a penstock. Now, in a lot of cases, this thing will also have an overflow from the forebay, because what we want to do is we want to maintain an exact pressure inside of this forebay. We want it to be always full, but never overly full. So we want any excess to be coming off the top if this thing is going to be overly full. Once we have a specific pressure, we're able to go and maintain rotational speed. So the rotational speed is going to be determined by basically the fall from over here, from the forebay, all the way down to the powerhouse. And inside of the powerhouse, we then run it through some type of a turbine. Usually micro hydropower is going to go and use impulse turbines. Less commonly, it will have reaction turbines. By then, that's just going to go and run from here. All the water goes through there. We generate the electricity, runs back into the house itself. This is going to go and result in a diversion. There are some where we actually place the generators directly into the water itself. This is going to be a Gorlov style water turbine. It looks very similar to our vertical wind ones. It's the same type of rotor that we are going to be able to use. This one is actually designed to go and run inside of ocean over here. So this one is going to be working off of a tidal one, this specific one over here. These are referred to as run-of-the-river. Run-of-the-river can be placed inside of the actual river. So in this case, all we would do is we would need a rapidly flowing river. We would place one of these inside of there, and any fish can still swim through. We're not damming up the river or anything like that. They're a little bit harder to go and maintain because often you do still need to have blocking things upstream of them, because otherwise you're going to get sticks and logs that are going to go through and jam them up. So they do require some of that maintenance. Okay, thermal systems. We don't have any illustrations here for thermal systems, but the thermal systems are going to be ones that we use heat. Now, remember, renewable energy is not supposed to be emitting greenhouse gases. We term renewable energy as anything that is not emitting greenhouse gases that would not normally be. When we burn coal or when we burn natural gas, that is us converting, those carbon-based substances into an actual, hydro, or into, we're burning them, and so we're creating, the carbon, the CO, etc., like that, greenhouse gases. Some processes are already going to go and create greenhouse gases, notably compost. So if you are ever working in northern BC, northern Alberta, you're going to see a lot of logging up there. Well, not so much these days, but in a lot of these log sorts and stuff like that, they have all these lumber mills, offcuts, the bark, all of that stuff would normally compost. And as it composes, it's going to release that carbon dioxide. We don't want it to release the carbon dioxide, but we can't help it. So rather than, just letting that carbon dioxide escape and getting nothing useful from it, we will go and use thermal mass, where we're going to go and, use a fire, usually start it with a bit of gas. natural gas, and then we're going to burn that, and as we burn that, we create heat, and we use that heat to go and boil water, which we change into steam, and then we run that steam through turbines. It is considered to be part of our renewable energy structure, even though it is burning components. Sometimes you'll refer to these things as being referred to as like biomass. There's other ones where they're going to compost and they're going to capture the methane off of it, and then they're going to go and run that through. If you go out to I guess it would be East Abbotsford out in the prairies there's a massive manure digester over there that's literally taking, feces from animals, mostly cattle, some chicken, actually some humans and stuff inside of there as well. They take in biosolids from some of these places, and they put it all in these giant tanks. These giant tanks have a huge rubber membrane over top of there. It looks like a big conical hat on top of it. And as it reacts inside of there's methane that's generated. They take that methane that's all captured underneath the big membrane top, and then they go and burn that. Once again, it's another form of renewable energy. Okay, fuel cells. Fuel cells are not widely used, but they are going to go and, be just a way that we're going to go and take energy and we're going to use it to convert it, change forms, right? Energy cannot be created nor destroyed. It can only go and change forms, which means that we can go from, chemical reactions or things like that would normally produce heat. Instead of them creating heat, we can use that to go and create electricity. And that's really what we're going to do with these. We are going to go and have membrane. So right over here, they identify this thing as the membrane that we are going to have over here. It's a proton exchange membrane that we are going to have in this case. What happens is that membrane is going to separate two sides, and those two sides are going to have two separate gases that are going to be placed through them. See this? This is going to be a solid component over here that's got channels through it. Those channels that are driven through there are going to be up against the membrane. And then I'm going to have on the other side this place over here that's going to have channels as well. It's harder to see those channels that are on the top, but they're little open channels like that. We're going to go and drive hydrogen through one set of channels. We're going to drive oxygen through the other set of channels on either side of these ones. And then what we will see is there's going to be a combination that is going to happen where through that membrane, which is permeable, meaning stuff can pass through, not everything, but where we're going to be able to go and pass the actual gases through here. The hydrogen, we're going to go and pass through this central part, the membrane electrolyte, and then it's going to combine with the oxygen to go and create water. If you've watched the movie The Martian, it's got, I forget the name of the actor, but he's stuck on Mars for some reason. Can't even remember why he got stuck on Mars or what he was doing there in the first place, but at some point he decides to grow potatoes and he needs water, and so then he creates a reaction. There's a little bit of a poof, a flame and stuff like that as he's combining a couple gases, then all of a sudden he gets this magical drip of water. The science doesn't quite check out inside of there, but what it is a combination of these two gases, the hydrogen and oxygen, that are creating water at that point. But in his case, the energy has to go and get dissipated in the form of heat. That's why there was that little flame that happened. In ours, we're going to go and say, hey, instead of us taking that energy out as heat, we'll take it out as electricity. We just provide a pathway for this thing. So what we'll have is we are going to go and take electrons. During this combination, there's going to go and be losses of some of our electrons. We're going to take those electrons out of one side and pass them through to the other side via a load. Let's draw that up top over here. They're showing us this light bulb over here. They show us one side that's going to be my anode. They show the other side that is going to go and be my cathode. The hydrogen, when we send the hydrogen in, it splits into individual atoms on this side over here, on the hydrogen side, which is always going to be my anode side over there. The electrons are removed, and so those electrons have to go somewhere. So those electrons are going to be removed as that chemical reaction happens, the split. And so those electrons are going to travel up through an external load, and then they're going to go and travel back through here. The hydrogen cannot pass through the membrane until its electrons have been split off. So we chemically split them off, pass those around to the other side. In the meantime, the ionized hydrogen is like, whoop, it can fly right through the inside of that membrane over there, where it then combines with the oxygen and with its electron again, and that combination produces water. The water will come out as being warm as well. We don't capture all of the energy, but we capture the bulk of the energy as electricity, and we're able to pass that through. They produce individual cells, and those cells are going to be able to be stacked together. So my individual cells are going to be about the same value as my photovoltaics, between 0.5 to 0.8, so roughly around the 0.7 that I'm going to go and have. We can go and monitor what's happening off of these. So this external circuit, if I go and place a ammeter around that thing and I place a voltmeter onto it, I can monitor the amount of electricity that is needed. And as I see my demand going up, I can increase the amount of flow that I would have of my hydrogen and my oxygen. This would be done electronically, and that's going to go and maintain optimal operation. As I slack off on load, I'm then going to be able to slow down the hydrogen and oxygen. We will have a polarization curve for these ones as well. If you look at my curve that I'm showing you over here compared with your curve inside the book, your curve inside the book just lost all the numbers and they went to dots. I have no idea why. But this one over here shows my cell voltage versus my current density. As I pull current through this thing, more current that is going to be pulled through there, I'm seeing a drop inside of my voltage. As I'm taking less current through, I'm seeing a rise inside of my voltage over here. So the basics behind those, they're not widely used. They are looked at for some of our components like transportation. They've been talked about for fuel cells to go and run vehicles, etc. The process of creating hydrogen and oxygen is also relatively easy. That can be done through electricity, hydroelectricity that I can take some other place, from a dam, and I can run that through water. And as I run that through water, I'm able to go and split it. I don't know if you ever build hydrogen. We used to do that, as kids. You'd go and build hydrogen with a battery charger, and then you would, strap fireworks to it. And you'd have like a whole 2-liter bottle full of hydrogen, and then you'd stick fireworks next to it. You get a big, big boom. Anyways, dangerous things you do as a child. But yeah, it's really easy to generate the hydrogen and the oxygen. Split those ones off. Okay, let's talk about power conditioning. Power conditioning units are going to be either synchronous or asynchronously tied. So once we generate that electricity, we need to go and make it something that is usable, because it's going to be coming in fairly crazy. It could be coming in at a high value of voltage and a low value of current. The frequency could be all over the place. And so what we need to do is we need to create a standardized system so that it is going to be usable. We are going to go and have inverters and power conditioning units. And it's going to go and take whatever we're generating and make it uniform. Converter, inverter, and charge controller all are going to have slightly different connotations, but they are going to be generally part of the same semiconductor class. Converters are going to go and take AC and they convert it to DC. Inverters are going to go and take DC and they're going to convert it back into AC. And charge controllers are going to go and regulate the amount of charge that we have on top of a battery, any type of a battery that we're going to go and have. Maximum power point trackers are also included inside of here. MPPTs are just going to be these things that will adjust, for some cases, because we want to go and have the maximum irradiance on a, solar cell. What we can do is we can place them onto a curved track and we can adjust that so it follows the sun. You can watch sped up ones of this, of solar farms, and you can actually watch these things tilt and rotate so that they're constantly following the sun. It's just going to be tracking where's your power at, and then it's going to be adjusting until it hits, these maximum peaks as well. The conversions that we will get will always have some losses. It is impossible to have lossless semiconductor units. They are fairly efficient. You usually are going to be able to get 80 to 90% minimum out of these things, but there will always be some losses off them, which means that you have to deal with heat that you are going to go and take care of. Some of them are going to be grid tied. That's this one over here, if you take a look at it. Grid tie central inverter is designed to go and have power that is going to be fed in from my renewable energy. That's going to be this one here. I'm just going to put down RE on this side. And then it's going to go and have power that is going to be fed in from my grid. I'm just going to put BCH over here for BC Hydro. And what happens is inside of here, this thing is going to go and match the grid frequency and voltage. We would never want to be unsynchronized from the grid, because then we couldn't flow anything that is going to be, inside of our system back out. So we always have to be tracking the grid itself. That renewable energy that is coming into here is going to be coming in as DC most likely. We'll convert it and we will go and resynchronize it with this, and then we will feed this thing back out onto our system. We can also tap off of it to feed our own individual loads, but in a lot of cases we feed it back out onto the system as well, and then we get what's referred to as net metering. We get a credit from BC Hydro on our bill rather than just getting a bill off of it. It is very important to note that these things need to have a reference for a grid tie. They cannot understand what to put for voltage or for frequency if they don't have hydro coming into these things. So they are going to be incapable of operating in a standalone situation. It's called islanding, where this thing would be operating even though my renewable energy itself might be operational. My solar cells, digesters, whatever I've got attached to that thing might be currently operating. If I lose power, this thing cannot go and provide power for my system. It is not a backup unit. It is just an alternative power supply for when the power is actually there and it drops your actual bill. So you need to always, separate these things inside of your mind from being, is it a backup versus is it an alternate source of power? If you're using grid tie, it is an alternate source of power inside of here. There's going to be microinverters as well that will go and directly detach to your solar cell. So over here, they're showing a partially completed solar installation. They've got the tracks that are up on a roof over here. The feet are tied down. They've got these plates on here. These plates are going to go and have a small little box. Hardly see it in the picture underneath here, but that small little box is going to go and have a plug-in for my solar cells. So my solar cell is going to go and plug in on one side, and then I'm going to be able to take my AC out of these things. They're just a standalone micro inverter. Do be careful that you understand what your inverter is going to go and be. If it is going to be a grid tie, it cannot go operate by itself. If you've got a hybrid inverter would mean that you could have lost your BC Hydro, but you would still be able to go and operate inside of there. You can use it as a backup system as well as a general system. Standalone inverters sometimes also have power that is going to be able to flow bidirectionally. In other words, we're going to be able to go and take DC in. Say this is DC in over here, and we're going to be able to pass it out as AC. But we're also able to take AC in and pass it out as DC. Once again, there's going to be specific applications where each of those are going to be, used. But if you are working on them, just be very aware that just because you shut down one side does not mean that it could not be backfed from the other or that it could not be converting in the other side. Over here, they've got a set of inverter chargers and a battery enclosure that are going to be placed over here. The battery enclosure is made out of plywood. It's got, sealing off of this thing. If you take a look up top over here, there's also going to go and be ventilation, because when we have got lead acid batteries, we generate hydrogen, which is a dangerous, gas. Think about those videos you saw at some point in history class of the Hindenburg, that big blimp that was on fire. That thing was full of hydrogen. You don't want, any of your plants going up like the Hindenburg, so you have to go and have some sort of way to go and ventilate. That's what we're seeing over here, is just that's ventilation pipe coming out of there. We're also going to go and have these sections over here. Now, this is a Xantrex set of controllers over here. That one is going to be an inverter charger. So we're going to go and take DC in. That DC that we are going to feed in, I don't know which one of these is DC because I can't tell from the picture, the connection inside. We'll call that one the DC. That DC is going to be able to go and flow in, and we're going to be able to go and divert it. Some of it is going to go and get converted to AC, and then we can go and flow it out. Some of it is going to get fed directly down into these batteries over here so that we can charge those batteries. Once we get the batteries fully charged, we don't send any more power to them, but it monitors the states. When I lose, any sort of power, when this thing would go and shut off, maybe I don't have any sunlight coming from my photovoltaics, at that point, my batteries would reverse. They would flow power back out, but it would still go through the inverter to the AC section where we can generate and drive it over to our actual loads itself. Excuse me. Alternators. An alternator is going to be something that is going to produce AC off of rotation. We sometimes refer to these things as generators as well. Don't get too hung up on whether you should be using the term alternator or generator. Specifically at this point, we'll cover that in depth once again inside of third year, what they are going to be. But what it is going to be a rotational machine converting into AC. Where that rotation comes from is going to be your renewable source. So this could be rotated by a water turbine. It could be rotated by your wind turbine. And as it rotates, we generate that electricity. Now, we do need to go and regulate the amount of voltage that we're going to go and take out. And one of the best ways to go and regulate voltage is just by regulating the amount of load. V is equal to I times R that I'm going to go and have. So if I want to go and maintain a steady value of voltage, what I need to do is I need to go and vary one of these if the other one is going to be changing. So let's start by saying that I is going to be my load current. If my load current would be going up, what I would need to do is I would need to somehow go and drop the amount of resistance that I would have on there so that I could maintain a value of voltage. And if my current would be going down, so I'm taking less power off of my generator, what I would need to do is I would need to go and raise the amount of resistance inside of that system to go and maintain a constant value of voltage. This is going to be referred to as a diversion load. We need to have a diversion load on some of our components that is just going to be a standalone, useless load to us, but that is going to be utilized to go and burn off extra power so that we can go and maintain our value of voltage. Commonly, what you will see these things looking like is just baseboard heaters. It's a very common type of diversion load where somebody's going to have a grid of baseboard heaters, just mounted in a shed, and anytime that there's too much power being generated, they're going to use that as the diversion load to burn off the extra so that their generators don't go and burn out. It's just heat that we just release back into the atmosphere, but it forms an electrical load for our generator. If I'm using DC storage like batteries, what I'll often do is I'm not going to worry so much about the frequency and the voltage that I'm going to be generating. I'm going to be generating at that point what we refer to as wild AC. And wild AC would be based usually off of these type of systems, where we've got a wind turbine. The wind's going really fast, it's spinning really fast, we get a high frequency and a high value voltage, but then the wind slows down, we get a low voltage and a low frequency. We call it wild AC because it's, harvested from the wild and could be all over the place. What I will do is I will use a permanent magnet alternator, and then that is just going to be generating AC. We don't care what the AC is because we're just going to convert it into DC and feed it into our battery bank, and then we take it out as DC and re-invert it back into what we want at that point. Induction generators, or what we refer to as asynchronous generators, is going to be grid tied that we are going to use. So synchronous generators don't have to be grid tied as much. Induction ones usually are. There are some cases where we don't have them, but in most cases, the asynchronous induction ones are going to be grid tied. We have not covered what the field rotation is, how that's generated inside of a motor or anything like that. You'll cover all of that inside of third year. But basically, if we can go and make the shaft of our motor or of our generator rotate faster than the field that's rotating inside of here. So I'm going to go and apply BC Hydro to the fields inside of here. And that BC Hydro, as we apply it to that field, is going to go and have a certain speed of rotation based on their frequency. If I can make this go faster than BC Hydro, it sets up a negative slip so that instead of this thing acting as a motor, it acts as a generator, and then we can feed that back into the system. But it has to always be going faster than what the Hydro one is going to be. You do have to be very careful with grid tie. Grid tie is not allowed to feed back in when BC Hydro goes down because it would not have anything to go and reference on this side. Plus, if the grid goes down, you're going to have lines like the lines themselves that are supposed to be dead. Whenever the hydro crews are going out there, they are expecting that those lines are dead. And if all of a sudden, you get a gust of wind, your turbine starts up and it puts voltage back on the line, you end up with, killing somebody from BC Hydro. They're not going to be very happy. We're not going to be very happy. It's just going to be this massive, massive problem. You can use them in standalone applications, but in that case, you need to have a completely different setup. You've actually got to go and add a whole pile of caps so that you can get a lagging magnetizing current in reference to the voltage over there. I know it sounds backwards to talk about lagging, but we're talking about, once again, that we're going to generate a current that's going to come off the caps over here that is going to be slower than what we have for our rotation over here. Okay, yeah, that's all that we're going to cover right now in this video over here. We're going to go and kick into another video where we're going to talk about the actual configurations of these ones. Just, the flow through, which is going to be all those block diagrams that we are going to go and have for the rest of it. But that covers our basics of how we generate renewable energy and what a lot of those components are. There's a huge section inside of your CEC on those ones.